Hi mathematicians, I'm going to try to do a better job of explaining linear equations. We'll see how it goes. So this is a first order linear differential equation, to be more specific. And I know that I can solve this so I can solve this if a naught of x equals a1 prime of x. If this is the derivative of this, then we're in business. Okay, most of the time that isn't true, but we can force it to be true by multiplying by an integrating factor. Okay, and so I'm going to show you where that integrating factor came from. So, put equation in standard form. Okay, so you're going to want to start by putting your equation in standard form. To put it in standard form, I'm going to divide everything by a1 of x because I want this leading term right now to be 1. So I get a1 of x divided by a1 of x dy dx plus a naught of x a1 of x y equals b of x over a1 of x. At this point, most textbooks rename this coefficient here p of x, and they just rename this term here q of x. Okay, so we started out first order linear differential equation. I know that if I can get it so that this is the derivative of this, I can solve it. So that's my goal right now. The first thing I'm going to do is I'm going to go ahead and put it in standard form. That means that I'm going to divide out this leading coefficient so that I have a 1 here. Now that I have this here, we are going to go ahead and multiply by integrating factor. And your integrating factor, u of x, equals e to the integral of px dx. And you're going to multiply, my cat is biting me. Stop. Okay. All right, sorry about that. So we're going to take this and we're going to multiply everything by this u of x. So we end up with a u of x dy dx plus u of x px y equals u of x q of x. Okay, where this equals our u of x. Now this is equal to this prime. Okay, so now we have u, and I'm going to rename it, I guess, 1 of x dy dx plus because when we multiply by this integrating factor, it makes this whole part the derivative of this. Okay, now that this is true, we get to go back and kind of undifferentiate this. So this is the result of implicit differentiation. Okay, so we're going to go ahead and take that dx out front. All right, and what we're left in there, what we're always going to be left in there is just our u of x y. Okay, because these are equal. Equals on the right hand side, you're going to have some new function, u of x, q of x. I'll put it here, sorry. Integrate both sides. The integral of this times the derivative of this just gives you this u of x y. Okay, so I know there's a lot of like goofy steps in here that might make your brain go. Okay, but in the end, on the left-hand side, you end up with u of x, y. You end up with that integrating factor times y on the left-hand side. And then on the right, whatever this might be, and then we divide both sides by u of x. Okay? And so then this y, this is some function that is going to make our linear equation true. Now I want to take a second and talk a little bit about where did they get this integrating factor, right? So we've written in standard form, and we have a dy dx plus p of xy equals q of x, okay? And I'm going to go ahead and multiply by u of x. So I get a u of x dy dx plus u of x p of x y equals q of x. What do I want to be true? I want u of x prime. I don't know why I feel the need to give that a 1 now, but I do. I want, oh, that's not. I want u of x prime to be equal to this u of x p of x. That's what I want, right? I want this to be the derivative of this. The derivative of this equal to this, okay? For that to be true, what do I need this to be? Let's go ahead and solve for this, okay? So I'm going to go ahead and change this to a dy dx, or excuse me, du dx equals, okay, right, this is just the derivative of u with respect to x, derivative of u with respect to x. I wrote down left-hand side, or the right-hand side. Now I'm going to cross multiply. We get du on the right-hand side. I get u of x p of x dx on the left-hand side. I'm going to go ahead and divide both sides by this u of x. So I get p of x d of x equals 1 over du. What do you think I'm going to do now? That's right, we're going to integrate both sides. So we integrate p of x d of x. We integrate 1 over u of x du. What do we get here? On the right-hand side, so on the left-hand side, we don't know what this is, right? I don't know what this function is, so I can't really break it down any further. I'm just going to leave it like this. What is this going to be over here? That's going to be an ln u of x. Do you feel okay about that? All right. Now, what did we want to solve for, right? The whole thing was up here. We're like, okay, what do we do to this p of x? If I have this u1 of x, u1 of x, p of x, how do I make this guy the derivative of this guy, right? So we're like, how do I make this statement true? I want u1 prime of x equal to this. That's what we've been solving. And now I want this u of x, but he's trapped in here. How do I untrap them? Well, if I raise both of these to the e, I'll get, and I'm just switching him to the left-hand side, u of x equals e p of x dx. Right? So we multiply p of x by u of x, and then to make this true. Does that make sense? Right, so we found a u of x that if I multiply it by everybody, oh, I already, did I give this guy? This guy's got to multiply over there too. I forgot about him. Pardon me. Right? So if I multiply everybody out, then that makes this true, that this is the derivative of this. Once that is true, then I can go ahead and solve like we showed you over here. Right? Once that is true, then I can go ahead and go through this. All right, let's do an example real quick. Been flapping my gums for a while. Just really doing symbolic manipulation and not actually doing doing a problem. So, here we go. Example. So we have 1 over x dy dx minus 2y x squared equals x cosine x. Okay, definitely first order, right? First order, linear. I have a y here. I have my first derivative here, okay? And so I know I can solve this if I can solve if negative 2x squared equals the derivative of that guy, right? So let's go ahead and see if it's true. It could be true. I don't know. Here, what is the derivative of this? So I have x to the negative 1. The derivative is negative x to the negative 2. Almost, right? But not quite. So here, I'm going to have negative 1 over x squared, not quite equal to negative 2 over x squared, right? But we're close. So what are we going to do? First, let's go ahead and put it in standard form. Standard form. Okay, because I already checked and it's linear, but this is not the derivative of that. So standard form, I'm going to divide everything by 1 over x. So I get dy dx minus 2 over x squared divided by 1 over x times y equals x cosine x divided by 1 over x. Okay, let's go ahead and clean this up. Dy dx. What does it mean to divide by 1 over x, right? If I divide by 1 over x, I multiply by, to divide by a fraction, you multiply by the reciprocal. So this is going to leave us negative 2 over xy equals, divide by a fraction, multiply by the reciprocal, x squared cosine x. All right, this is my p of x. This is my q of x. So now, step 2, we're going to multiply by u of x. By multiplying by u of x, we're going to make sure that u of x, of course, is going to pop out here, and then its derivative is going to be here. Okay? So my u of x in this situation equals e to the integral of negative 2 over x dx, right? And we're going to go ahead and we're going to multiply that through with everybody, but I'm actually going to kind of hold on to it until the end, if you want to know the truth. So This, let's finish this off so we don't have to think about it later. This is going to become e to the negative 2 ln x, and then that becomes x to the negative 2. All right, so let's go ahead and we're going to get u of x dy dx. This is what I mean by I'm just going to hold on to this for a second. Hold on to it. Okay, and then I'm going to go minus u of x 2 over x y, right? I'm just multiplying this guy in, equals u of x times x squared cosine x. All right, when I do this, I know that this is the derivative of this, and so I can go ahead and just write this as u of xy d dx. Running out of room. Equals, now I'll go ahead and write this out. I get my x to the negative 2 x squared cosine x. Cross, cross. We're going to integrate both sides. With respect to x, you get u of xy equals the integral of cosine x dx. Oh, I need a new piece of paper. Okay, let's see. We'll keep, kind of try to slide it up here. Y is going to equal 1 over u of x. What's the integral of cosine x? Sine x plus c. And so this is going to end up being x squared sine x plus x cx squared. Yeah, great. Okay. Integral of cosine x is sine x plus c. Then I divided by u of x. U of x, what was u of x? Oh, right up here. X to the negative 2. If I divide by x to the negative 2, it just becomes x squared. And I have to distribute that to both of these. Okay, and so we found the solution. And so just to go over this again, this is a linear first order differential equation. I can solve it if the stuff in front of the y is the derivative of the stuff in front of this guy, the first derivative. Okay, so the first thing I did here is I checked. I was like, is the derivative of 1 over x equal to negative 2 over x squared? And it's not. So I was like, okay, now I have to use an integrating factor. Now that I have to use an integrating factor, I went ahead and I put it in standard form first. To put it in standard form, I just divided everything by this 1 over x, right? I had 1 over x here. That, of course, goes to 1. You want that leading coefficient to end up being 1 in standard form. I divided here, right? Dividing by a fraction is the same as multiplying by a reciprocal. That gives me negative 2 over xy equals, again, dividing by a fraction is the same as multiplying by its reciprocal. You get 8 squared cosine x. This is a q of x, okay? Sometimes you'll hear people say that's q of x, and this is my p of x. Now we're going to multiply by a u of x. This is our integrating factor. When we multiply by this, we end up with a u of x here. We end up with the derivative of u of x here. And then, of course, some funny function over here that doesn't bother us. Okay? By doing that, okay, so the integrating factor, it's going to be e to the integral of whatever is in front of this y here. So we got x to the negative 2. So now we're going to multiply it here, multiply it here, multiply it here. Sometimes I forget to multiply it over here. Don't forget that. I do that a lot. Okay? But I'm not going to get too bogged into actually doing any multiplication yet or anything, because I know that because I did this, I can just go write d dx u of xy, and then I'm just going to end up with the u of xy over here. Now that I have this, now I can separate, right? And so we take of course, we took the integral of both sides here, get this out. You have your integral, and then you divide by u of x here. Okay? And then we finished it up. Let's see if I can line this back up here. Right? We distributed this out, and that's this is a general solution. How do I know it's a general solution? This has a c in it. Right? And we can solve for values of c. Say we wanted the initial condition, we want y of 0 to equal 1. Oh, that's not going to work out. Okay. How about the y? We want the y of... Do you want to talk in radians or degrees? Let's talk 2 pi. Okay, we want the y of 2 pi. How about that? To equal 1. I think we could solve that. All right, so we want y of 2 pi equal 1. Y of 2 pi equals 2 pi squared sine 2 pi plus c 2 pi squared. Okay, what is the sine of 2 pi? It's 0, so that whole thing gets to be 0. We want that to be equal to 1. And then we have c 2 pi squared. So in this situation, c is going to equal 1 over 2 pi squared. Okay, and then that y equals is the particular solution, right? I just plugged in for c. The particular solution for y at 2 pi equaling 1. All right? I hope that was helpful.